Hello everyone. Today I am going to deliver third lecture. The topics are Feedrate Selection, Feedrate Control, Feedrate Function, Feedrate per minute, Feedrate per revolution, constant feedrate. If you had not seen my first and second lecture, so go to the description and click on the link. First of all, you have to understand the spindle speed and cutting speed, then you have to watch my third lecture. So now let us start Feedrate selection. To select the best feed rate, one that is most suitable for a given job, some general knowledge of machining is useful. This is an important part of programming process and should be done carefully. A feed rate selections depend on many factors, most notably on a spindle speed, tool diameter or the tool nose radius, surface requirement of the part, cutting tool geometry, machining forces, setup of the part, tool overhang, length of the cutting motion, amount of material removal, method of milling, number of fluids in the material, safety consideration. The last item is safety, always a programming responsibility number one to ensure the safety of the people and equipment. Safe speeds and feeds are only two aspects of safety awareness in CNC programming. The next topic is your Feedrate control. Feedrate is the closest programming companion to the spindle function. While the spindle function controls the spindle speed and the spindle rotation direction, Feedrate controls how fast the tool will move, usually to remove excessive material. Cutting feed rate is the speed at which the cutting tool removes the material by cutting section. The cutting action may be a rotary motion of the tool, drilling and milling for example. The rotary motions of the part, lathe operation or other action, flame cutting, laser cutting, water jet electrical discharge, etc. The feed rate functions is used in the CNC program to select the feed rate value suitable for the desired action. Two feed rate types are used in CNC programming. The first is your feed rate per minute and the second is your feed rate per revolution. The most common type of machines, CNC machining center and lathe, can be programmed in either feed rate mode. In practice, it is much more common to use the feed rate per minute on machining center and the feed rate per revolution on the lathe. There is a significant difference in G code used for machining center and lathe. So feed rate as per minute, so milling is your G94, turning group A G98, turning group B G94, turning group C G94, and feed rate per revolutions, milling G95, turning group A G99, turning group B G95, turning group C G95. The G code group A is the most commonly used on Fanuc control. Another type of a special feed rate is called the inverse time feed rate. It is very seldom used and it not discussed in this lecture. In milling, the programming control G code for the feed rate per minute is Z94. For most machines, it is set automatically by the system default and does not have to be written in the program. For lathe operations, feed rate per minute is used very seldom. In group A, the G code for feed rate per minute is Z98. For group B and C, it is Z94. CNC lathe use primarily feed rate per revolution mode. The next topic is your feed rate function. The calling address for a feed rate would in the program is the address F followed by a number of digits. The number of digits following the address F depend on the feed rate mode and the machine tool application. Decimal place is usually allowed. So feed per minute For milling application, all cutting feed rate in the linear and circular interpolation mode is programmed in inch per minute or in millimeter per minute. The value of the feed rate is the distance a cutting tool will travel in 1 minute. This value is modeled and is cancelled only by another F address word. The main advantage of the feed rate per minute is that it is not dependent on the spindle speed. That makes it very useful in milling operation using a large variety of tool diameter. Standard abbreviations of feed rate per minute are inch per minute, millimeter per minute. The most typical format for feed rate per minute is F3.1 for the English system and F4.1 for the metric system. For example, the feed rate of 15.5 inch per minute will be programmed as F15.5. In the metric system, the feed rate amount of 250 mm per minute will appear in the program as F250.0. A slightly different programming format may be expected for a special machine design. One important item to remember about feed rate is the range of the available feed rate value. The feed rate range of the control system always exceeds that of the machine servo system. For example, the feed rate range of a Fanuc CNC system is between 0.0001 and 24,000.0 in inch per minute or 0.0001 and 240,000.0 millimeter per minute. Note that the difference between the two units is only a decimal point shift, not an actual translation. In programming, only the feed rates that belongs within the specified range can be used. Such a feed rate will be smaller than that for the control system. The next topic is your constant feed rate. I am going to details explanation and example of the maintaining a constant cutting feed rate for inside and outside arcs from the practical point of view. At this point, the focus is on the understanding of the constant feed rate rather than its application. In programming, normal process is to calculate the coordinate value for all the contour change points. Based on the part drawing, the cutter radius that produces the center line of the tool path is typically disregarded. When programming arcs to the drawing dimensions rather than to the center line of the cutter, the feed rate applied to the programmed arc always relate to the programmed radius, not the actual radius cut at the tool center. When the cutter's radius offset is acting and the tool path of the arc is offset by the cutter radius, the actual arc radius that is cut can be either smaller or larger depending on the offset value for the cutting tool motion. It is important to understand that the effective cutting radius will decrease in size for all internal arcs and it will increase in size for all external arcs, since the cutting feed rate does not change automatically during the cutter radius offset mode. It must be adjusted in the program. Usually, this adjustment is not necessary except in cases where the surface finish is of great importance or the cutter radius is very large. These considerations applies only in circular motion, not to linear cutting. In normal programming, the linear feed rate is used for arc as well as determined by the machinability rating for the given material. So first, here in the standard formula for calculating a linear feed rate. So FL equal to revolution per minute multiple of FT multiple N. So where FL is equal to linear feed rate, so this is your inch per minute or millimeter per minute. Revolution per minute is your spindle speed, FT is your feed rate per tooth, that is your cutting edge, and N is the number of cutting edge fluids or insert. In the various countries written in the same equations in different manner. So in the calculating table feeds, the metric equations would look like this. So here we are looking at F equal our table feed. If Fz is our feed per tooth, N is our spindle speed in revolution per minute, and set is the number of teeth on our milling cutter, and the Imperial equations is exactly the same. What makes it Imperial is our feed per tooth would be in inches and not in millimeter. So our key for this would look like this. As I have just explained, both equations will be the same for metric and Imperial. So F is our table feed. The what we are trying to calculate F said is the feed per tooth. N is our spindle speed in revolution per, and Z is the number of teeth on our milling cutter. Now our feet per tooth, you might see this written in different ways depending on which countries and which source you are using to see your information. So this changes, and we should not get too confused about number. Really is just empty box that we are going to put number in that holds the numbers for our equation. So what we call these empty boxes, what our key is not that important, and it will change depending on what source you get your information from. Now I have used the same abbreviations that Sandvik supply on the back of the tooling packet. Now I have done this for easy because I tend to always use Sandvik tooling when I am working most machine shops. I have worked for well VC Sandvik, so over the years these keys here, these abbreviations have been kind of standardized in my brain. This is the ones I see the most often when I am using these abbreviations in the workplace. So these abbreviations would be on the back of any tooling information. It would be in the Sandvik catalog. This is what your tool rep from Sandvik would supply you when you ask the tool rep for information about cutting a speed. So I am taking feet per tooth as FZ. You might also see it called a chip per tooth, which would be abbreviated to CPT, or quite often or chip load, which could be CL. It could be inch per chip, it could be millimeter per chip, whatever, but it does not matter. It is just an empty box to hold our value, so we can do an equation. Okay, so the feet per tooth, this basically means the amount of material we would be removing by each tooth as it removes material from our part. So let us have a look at how we are going to do this equation. So now I have go to the explain here problem number 1. So a spindle speed of 500 revolution per minute and a slot drill with 3 teeth. What feed rate should be used with a feet per tooth of 0.002 inches? Okay, so we need to find our table feet, which is F equal feet per tooth, which we abbreviated them to F set in this case. Now feet per tooth, you get this information from your tooling supplier. It would be on the back of the tool packet, the same as the cutting speeds and the feet per tooth. They have spent much time calculating and testing to get this figure. So it will be most accurate getting this information from the supplier of your tool than from a random number you find on the internet. That is what we are going to do because we are not using this for any particular tool manufacturer. We can come up with some ranges to put in here that may be relevant. So in Imperial, for example, our N value, that would be the spindle speed, and we just worked out the spindle speed in a previous lesson, how we can define that, and all that is again times by the number of teeth on our table. So if we use a slot drill with 2 teeth, we would add 2 here, or if we were using a 4 tooth end mill, for example, we would use for the 4 in this value here. So now we have got a value or a temporary value for our feet per teeth. So we can work out this equation. So let us say F is equal to 0.002 of an inches, and we will times that by our spindle speed. Let us give it a spindle speed of 500, which we worked out already using a spindle speed calculation, and then we can times that by, so we are using a cutter with 3 teeth, so we can times that by 3, and that is our equation to get our feed rate. So now feed rate of 3 would be 3 inch per minute. So now let us start problem number 2 with a feed rate per tooth of 0.2 mm and a spindle speed of 500 revolution per minute. So calculate the feed rate for a tool with 2 teeth. So here let us look at one in metric. Okay, so we have a metric program and we want to work out our table feed. So for that we would use same equation, of course, F now equal our feet per tooth. Now we are working in metric this time. Now if we look on the back of our tool packet, we might find a feet per tooth ranging from 0.1 of a millimeter to say maybe 0.5. So if we use 0.2 of a millimeter for our feet per tooth, So we are going to make up that's what's written on the back of the tooling packet that is recommended for this cutter that we have been sold. So we use a metric value this time. So our feet per tooth would be 0.2 of a millimeter, and then we would times that by the spindle speed. I am going to use the same spindle speed as before, 500, and we are going to times that by the number of teeth. So let us say, for example, this time we are using a 2 flute slot drill. We are going to times that by 2 because we have 2 teeth on our slot drill. So we can pop that informations into our calculator again. So we are looking at 0.2 times 500 times 2, and that gives us 200 millimeters per minute. So that is how we work out the table feed in metric. So the only information that we need help with is finding our feed per teeth, and we would get that from the tooling manufacturers, and it is normally supplied on the box that the tool comes in. So let us do another example in inches. Again, let us do an Imperial example. So my problem number 3 is your, if our cutter has 4 flutes with a feed per tooth of 0.004 inch, what is the feed rate with a spindle speed of 2000 revolution per minute? So that is, take F is our table feed. So now to find feed per tooth, let us use for 0.004 inch this time. So let us say our back of our tool packet see the best feed per tooth filling material, and we would times that by our spindle speed. Let us give it a much faster spindle speed. This time let us say we are cutting at 2000 revolution per minute. Now feed per tooth, let us say we are using a cutter with 4 teeth. Okay, so now we just all that into our calculator, and it tells us will our table feed should be our recommended table feed. Now remember, these are recommended areas to start from. Once we have punched it in the machine and we start taking a cut, we might feel it is a little bit too fast or a little bit too slow. It might be not giving us quite the surface finish we require. So we would add or subtract a little bit to this. It just gives us a starting point to get a feel for what the materials like to cut. So if we do this equation for 0.004 times 2000 times 4, it will give us a feed rate of 32 inch per minute. Okay, so let us have a look at one more example in metric. So now next is my problem number 4. Using a 3 flutes end mill with a feed per tooth of 0.3 mm, what feed rate would be used with a revolution per minute of 800? So for the metric example, we are calculating our table feed and our feed per tooth. Let us say this time is 0.3 of a millimeter. So we are using a slightly softer material. We can go a little bit faster. So maybe it is how the aluminum or sometime like that. So the recommended feed per tooth on the back of our tool packet recommended 0.3 of a millimeter. So we can times that by our spindle speed. Let us say this times we are cutting it 800 revolution per minute, and then we would times that by the number of the teeth of our cutters. Let us say we use the 3 flutes cutter, and then we would be to the equations. So this would be, let me get my calculator out. So we are looking at 0.3 times 800 revolution per minute, and we times that by the 3 teeth in our cutter, and that would give us 720 millimeter per minute. So that is how we could calculate our table feed for a metric program. There is been 4 examples there and maybe some practice questions, so you can go over less and make sure you understand fully what is going on. And when I supply with practice questions, I will give you the answer, because it is the working out that is important. As long as you have got the answer, you can know whether your working out is correct or not if you arrives to the same answer, and I did. So that is how we calculate our table feed in both metric and imperial on a milling machine. So now important features of a linear feed rate: 4000 revolution per minute, 0.0045 inch per tooth load, and 2 cutting edges. The feed rate is 9 inch per minute. So using relatively large cutter diameter such as 0.625 inch, that means your 0.625 multiple of your 25.4, it gives your 15.875 millimeter or longer. The linear feed rate adjustment up or down for circular motion may be necessary to maintain good finish. So based on the linear feed rate formula, the arc feed rate adjustment is influenced by the side of the machined arc, outside or inside. The linear feed rate should be increased for outside arc and decrease for inside arcs. The next topic is the feed rate per revolution. There is a significant difference in G code used for machining center and lathe. For the CNC lathe work, the feed rate is not measured in terms of time, but as the actual distance the tool travel in one spindle revolution, that is rotation. This feed rate per revolution is common on lathe G99 for group A. It is value is model and another feed rate function cancels it, usually the G98. Lathe can also be programmed in feed rate per minute G98 to control the feed rate when the spindle is stationary. The programming control for the feed rate per revolution is G99. For most lathes, this is the system default, so it does not have to written in the program unless the opposite command G98 is also used. It is relatively more common to program a feed rate per minute G98 for a CNC lathe program than it is to program a feed rate per revolution G95 in a milling program. The reason is that on a CNC lathe, this command controls the feed rate while the spindle is not rotating. For example, during a bar feed operation, a part stopper is used to push the bar to a precise position in the chuck or a collet, or a pull put finger to pull the bar out. Rapid feed would be too fast and feed rate per revolution is not applicable. Feed rate per minute is used instead. In case like this, the G98 and G99 commands are used in the lathe program is required. Both commands are model and one cancel the other. Two standard abbreviations are used for feed rate per revolution. So inch per revolution, millimeter per revolution. The most typical format for feed rate per revolution is 4 decimal places in the English system and 3 decimal places in the metric system. This format means the feed rate of 0.083333 inch per revolution will be applied in the CNC program as F0.0833 on most controls. The metric feed rate examples of 0.42937 mm per revolution will be programmed as F0.429 on most controls. So many modern control systems accept feed rate of up to 6 decimal places for English units and 5 decimal places for metric units. Be careful when rounding feed rate values. For turning and boring operation, reasonably rounded feed rate are quite sufficient. Only in single point threading, the feed rate precision is critical for a proper thread lead, particularly for long or very fine threads. Some fun controls can be programmed with up to 6 decimal places feed rate precision for threading only. On the CNC life, we work in feet per revolution and not feet per minute as we do on a milling machine. So this equation teaches us how to convert between feet per minute and feet per revolution. So let us have a look at the formula, and feet per revolution is what did Fn equal. So now F is our table feet and N is our spindle speed. So it is work out our feet per revolution. We take our table feet and we divide it by our spindle speed. Now this equation is an Imperial. It looks exactly the same. What makes its Imperial is the table feed that we give. If we give it a table feed in metric, it will give us a metric answer, and if we give it a table feed in Imperial, it will give us an answer in inch per revolution. So let us do some maths and have a play with this equation to see how it works. Okay, so we need to find the feet per revolution, so we need to find Fn. So let us do this one in Imperial. So now my next problem is given there. So with a table feed 3 inches per minute and a spindle speed of 500 revolution per minute, what is the feet per revolution? So let us say our table feed is 3 inch per minute and we use the spindle speed of 500 revolution per minute. So 3 divided by 500 with equal 0.006 of an inch, and that is per revolution. So every time the spindle goes round once, the tool will progress by 0.006 of an inch per revolution. So that is how we account our feed per revolution on a lathe metric example. So now the next example is a spindle speed of 1000 revolution per minute and a feed rate of 200 mm per minute would give us a feed per revolution of. So let us say our table feed is 200 mm per minute. In this case, okay, so our equation would look like this. Our feed per revolutions would equal 200 our table speed divided by our spindle speed. Let us give it a spindle speed of 1000 revolution per minute this time. So 200 divided by 1000 would equal 0.2. So our Fn value for this would be 0.2, and that is in millimeter per revolution exactly. So that is how we calculate this in metric. So what we need in our table feed, we need to know that variables to be able to complete this, and we also need to have an idea of what our spindle speed going to be, and that give us our revolution to set the machines. So when we are using a CNC lathe, I first learned this technique using manual lathe to convert a feed rate to work on a manual machine. So let us have a look at another Imperial one. So my next problem is if our spindle speed is 1500 revolution per minute and we have a feed rate of 32 inches per minute, calculate the feed per revolution. So Fn again is our table speed. Now remember, you might see these variables called a different name depending on what education and what country you are in. We tend to use this as a placeholder for a number, and they do tend to change, and I have seen this used in all sorts. I have seen this represented in many different way, but we use an Fn here. It does not affect the equation. The maps is still the same. It is just the way we are marking our variable in the equation. So if n and if we are going to be used in a table feed of maybe say 32 this times, and we use an Imperial, so this is inch per minute, that is really fast table feed, and we use the spindle speed of 1500. So this is going to give us quite a fast feed rate, I would say. So 32 divided by 1500 would equals 0.0213. So we are looking at 0.023 in inch per revolution because this is an inches. So we are looking at a really fast feed right there, but that is the feed rate we would get from a table speed of 32 inches per minute with a spindle speed of 1500. Okay, let us do one last one in metric to make sure we really understand this concept. So the another problem is a feed rate of 720 millimeter per minute with a spindle speed of 2000 revolution per minute would give us what feet per revolution. Okay, so this times we did a metric example. So our Fn, let us give it a table speed of 720 millimeter per minute this times, and we are going to be divided that by a spindle speed to 2000. Let us go with 2000. So if our table feed is 720 millimeter per minute and we have got a spindle speed of 2000 revolution per minute, so we would divide it 720 by 2000. So our Fn value of our feet per minute would equal 0.36, and that is millimeter per revolution. So for every revolutions of a spindle, that would travel 0.36 of a millimeter. So that is how we do feet per revolution. It is quite a simple equation, this one. It is CNC or manual. The equations is still the same, and this is how we work out our feet per revolution when we got a good idea of what table speed we wish to achieve. Congratulations, you have made it to the end of this topic's feed rate calculation first part. So now you have a understanding of how to calculate feed rate for your CNC machines. Carry on the study in this area. So thank you again, and I shall see you in the coming topics: circular motion feed rates, feed rate for outside arcs, feed rate for inside arcs, maximum threading feed rate, maximum feed rate considerations, feed hold and override, feed per tooth, that is the chip load, and cutting time.